Hello, geometry. How are you doing? This is our second assignment for this week. So it's week 2. It's the second assignment. This is what I'm going to call 2.2. We're going to look at the last little bit of similarity things going on here with some triangles. And this technically is like section 12.3 in the book. Just letting you know. Let's jump into our first theorem real quick. So this is the triangle proportionality theorem. Basically what you have is if you've got a line that is parallel to a third side of a triangle, it's going to be cutting the other two sides into proportional. It's going to be cutting them proportionally, excuse me. So here I see it says if a line parallel to one side, so I'm going to write this out kind of in shorthand. If I have, and in the figure we have DE being parallel to segment BC. If DE is parallel to BC, yada yada, then it intersects the other two sides, then it divides those sides proportionally. That means we have the same proportions between this intersection and this intersection here. It's the same proportion as this intersection to that little segment guy there, all right? So, finishing this little shortcut off, if segment DE is parallel to BC, then the ratio of AD to DB, this segment here, that ratio has to be equal to the ratio on the other side as well. So that has to be equal to the ratio of AE to EC. All right, so if you have a parallel line cutting your triangle, kind of sliced right down the middle, then it's going to divide those sides proportionally. I would highly suggest that you have maybe a sketch of this figure and also write down that ratio as well, because that might help you. All right. Let's take a look at an example real quick. Oh, before I do that, let's just talk about the converse. So this is like an if-then statement, right? So the converse, you just flip these around. So the converse of this thing would be if you have this proportion between the sides. Let me write this out. If AD over DB is equal to AE over EC. So if that proportion exists, then you can say that DE is parallel to BC. All right, I'm really concerned that you know that if you've got this parallel line coming through here, all right, then it splits our sides proportionally. Okay, I kind of drew a lot on that. Hopefully that made sense. So down here, we're going to find the value of x. And if we look at this, we do see that we have parallel lines here. So I know I can set up this ratio, right? There's going to be this 6 to the length of x has to be the same ratio as 8 to this length of 4. So if I kind of follow this right up here, right, I can plug in these values. This 6 would kind of like go in for AD because you see that it's this top length. I'm just kind of following the picture here. And also my X would go in for this bottom one. Again, we're kind of following this picture down here just to make it easy on ourselves. So I'm just going to get rid of this so we know what we're talking about exactly. This ratio 6 over X has to be the same ratio of 8 over 4, comparing those sides since it is split proportionally. And then we can just solve for x real quick here. And if you think about it, this side over here, like 8 over 4, that's 2. That simplifies down to 2 because 4 goes into 8 twice. So what number goes into 6 twice? It should be 3. Let's do some math on that real quick to confirm. So I'm going to cross multiply to solve for x. I'm going to do 6 times 4 is 24, which equals 8 times x, and then divide by 8 on both sides, and you got that x equals 3. So yes, indeed, we do have that length of 3. So x is equal to 3. Okay, let's look at this next one down here. I'm asking what is the value of x again? And we also have some more questions. Are some triangles in here possibly going to be similar, and what theorem would we be using if they are? So what is the value of x? Again, I'm going to kind of look at these here and say, well, I've got these parallel lines that run through here. So I know that these parallel lines have to split my other two sides proportionally. So again, I'm going to kind of color code these sides that are going to be proportional. So this proportion of 6 to 2 is going to be the same proportion as 9 to x. So I'm going to set this up and say 6 over 2. So like my orange over my green has to be the same as my orange over my green here. Again, keeping consistent with that ratio, being able to set up this proportion. So 6 over 2 is equal to 9 over x. Again, we can cross multiply here. And again, if you think about it, this fraction right here simplifies down to 3, right? Because 6 divided by 2 is 3. 2 goes into 6 3 times. So what number goes into 9 3 times? Well, if we think about it, 9 divided by 3 is 3. So x should be equal to 3. Let's do some math again and confirm that. Alrighty. So I'm going to cross multiply. I'm going to say 6 times x equals 9 times 2. What do we got? 6 times x equals 18. Divide by 6 on both sides, and I get that. Oh my gosh. What did we say? Did we say x equals 3? We did say x equals 3. We are good to go. So I've got this x equals 3 here. And now my question asks, is triangle PST similar to triangle PQR? Give me just a second here. I'm going to replace this with 3 since we know that length is 3. There we go. All right. So it's asking, would this triangle PST be similar to triangle, do it in orange, be similar to triangle PQR? Would those two triangles be similar? What did we talk about in the last lesson in 2.1? We had some shortcuts that showed that some triangles are going to be similar. Like we had angle, angle. Do we know two angles in these triangles that would be congruent? No, we only know like one of them right now, right? I mean, just looking at this, we only have one triangle or one angle that's shared between the triangles. What was the other one? Side, side, side. Do we have all the sides in a common proportion? Again, right now, just by looking at it, we don't know the length of QR and we don't know the length of ST. So I'm going to say we can't use side, 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 but we do have this length of, or we do have an included angle at this like angle P. Oh, I just lost everything. We do have this angle that's included at angle P. And if we could figure out, would these sides be proportional? Well, and if you think about it, we just said that this thing is like, it's dividing our segments into proportional sides, but this entire length would be a length of 8, and this entire length would be a length of 12, correct? So if I had to set up these proportions between my sides, between this PS side of 6 and the PQ side of 8, so I'm going to say my smaller side to my bigger side, so 6 over 8, this ratio between those sides. Is it going to be the same ratio as my smaller side, this 9, to my bigger side of 12, 9 over 12? Is that going to be the same? If we simplify this down, that is going to be a ratio of, of 3/4, excuse me. Simplifying that down again, oh my gosh, you get a ratio of 3/4. So yes, our sides are in a common proportion. We do have that the angle that's included here is going to be, it's going to be the same since it's literally the same angle right here, right? So that angle is the same. These sides are in a common proportion. So yes, those two triangles are similar to each other, and we use the SAS triangle similarity theorem. Alrighty, wonderful, wonderful. Alright, the homework for 2.2 is going to be page 388, number 2, number 3, number 4, and number 7. 4 short problems should be pretty simple. They're following very similar to the lesson that you just watched. If you do not have your book or you don't know how to do online access, which I do have a video on my YouTube channel to show you how to do your online access to get your book, I did type up all the questions and they are going to be available in the Google Doc posted in the assignment. Alrighty, have a great day and I will see you later. Adios.